Hi everyone, this is Maths for Uni. This is the work solution to question 4 from the worksheet corresponding to lecture 3. If you find this content helpful, then please consider liking the video and subscribing to our channel. The question says, given the matrix A, which is 1, 0, 1, 1, calculate a squared, a cubed, and a to the 4, and then state and prove by induction the general result for a to the power of n, and by n it means some natural number n. So firstly, let's calculate a squared. This is going to be 1, 0, 1, 1 times 1, 0, 1, 1, i.e. a times a, and by expanding out the elements we have 1 times 1 plus 0 times 1, so 1, and then 1 times 0 plus 0 times 1, so 0, 1 times 1 and 1 times 1 added together, so 2, and then 1 times 0 and 1 times 1, so 1. Similarly, if we continue, next we have a cubed, and we can get this by doing a squared, so 1, 0, 2, 1, times a, which is 1, 0, 1, 1. And again, if we do this, we will get 1, 0, 3, and then 1. Lastly, if we do a to the power of 4, then we could say do a cubed times a, or we could do a squared times a squared. Let's do that to mix it up slightly. So 1, 0, 2, 1 for a squared times a squared. And that gives us, let's have a look, 1, 0, 4, and then 1. So hopefully you can start to see the pattern that's happening here. When we had a to the power of 1, that was just 1, 0, 1, 1, and then a squared, a cubed, and a to the 4 look exactly the same, except the element down here changes from a 1 to a 2 for a squared, to a 3 for a cubed, and to a 4 for a to the power of 4. And so we would conjecture, based on this pattern, that a to the n would be 1, 0, n, 1. And again, this is just a conjecture. We haven't actually proven this yet, but we can prove this result by induction, as suggested in the question. If we're going to prove this result by induction, then we should start by considering our base case, which in this case could be n equals 1. So we have a to the power of 1. We know from our original definition of a was 1, 0, 1, 1. And again, that agrees with the above for n equals 1, just putting n equals 1 into there. So indeed, our base case is satisfied. Next we have our inductive assumption, which is, let's have a look, that a to the power of n is 1, 0, n, 1 for some particular value of n that we're considering. We're not saying this is true for all values of n just yet, that's what we're proving, but instead for a particular fixed value of n. Normally, to be less confusing, some people say assume the result is true for n equals k, and then look at n equals k plus 1, but usually in maths we just take n and never even consider any kind of k. So we have this result is true for a particular fixed value of n, and then we do our inductive step, where we look at a to the power of n plus 1, and try and show that it has the required form, i.e. the above here, but instead n is replaced by n plus 1. So how can we compute a to the n plus 1? Well, a to the n plus 1 is equal to a to the n multiplied by a, just from the adding of the powers. This is secretly a to the power of 1 here. And so we can use our inductive assumption on a to the power of n, namely we have this result here. So a to the n is 10n1, and a to the 1, we know from our original definition, is 1011, and then we multiply these out, and we will get 1, 0, and then, as required, n plus 1, and then lastly 1. Therefore, indeed, we have shown what was required for n plus 1, and therefore, by induction, a to the n equals 10n1 for all natural numbers n. And so, I will use a square box to conclude our inductive proof. If you enjoyed this video, then please consider liking and subscribing. Thanks for watching, and goodbye for now.